All right, today we are diving into a paper that really shook things up in the world of AI vision. It's called SimCLR, and it's built on an idea that is so simple yet so powerful it almost feels like magic. Let's get right into it.
Take a look at this picture. Easy for us, right? It's a dog, but think about it for a second. How could a computer ever learn that without being spoon-fed millions of other pictures that humans have painstakingly labeled dog? This has been one of the biggest roadblocks in AI, and it's the exact problem SimCLR is designed to solve.
You see, for a long time, the main playbook was something called supervised learning. And honestly, it's a grind. It means paying tons of people to sit there and manually label mountains of data. This is a car, this is a tree, this is a cat. It's incredibly slow, it's super expensive, and it was becoming a massive bottleneck holding the whole field back. So what's the alternative? What if the AI could just learn from the raw, unlabeled images floating all over the internet? This is the promise of what's called self-supervised learning. Instead of waiting for human labels, the model makes up its own homework, its own learning tasks, right from the data itself. The way SimCLR does this is through a really beautiful idea called contrastive learning. And the intuition behind it is actually very human. We learn about what things are by comparing them. You know what makes a dog, in part because you know how it's different from a cat, or a chair, or a car. So how do you get a computer to do that? Well, you tell the AI to create a sort of digital fingerprint for every image it sees, a representation. And the goal is super simple. Make the fingerprints for similar images look really, really similar, and make the fingerprints for different images look, well, totally different. That's the entire game. So how does this actually work in practice? When you strip it all down, SimCLR is basically a clever matching game. It's like a game of memory, but for a neural network. It has to figure out which two pictures in a huge pile are just different versions of the same original image.
The whole process breaks down into 4 really straightforward steps. You start with one image, you make 2 tweaked versions of it, you run them through a network to get those digital fingerprints, and then you make the network play the matching game. Let's walk through that.
First, we just grab an image, any random, unlabeled picture from a huge dataset. No human has to tell us what's in it. That's the whole point. Okay, next comes the magic trick. It's called data augmentation. We take our one original image and we create 2 randomly altered versions. Maybe one's cropped differently, the other one has its colors all distorted. The most important thing is that the AI knows that these 2, this positive pair, came from the exact same source. And this is the game. You take that positive pair and you toss it into a big lineup with a bunch of other random augmented images. We call those negative examples. The model's only job is to figure out which 2 are partners. And to win, it can't just look at simple stuff like colors or textures. It has to learn the deeper features that truly define what's in the image. The paper itself puts it perfectly. The entire goal is to maximize agreement between the digital fingerprints of those 2 positive views. You want to pull them as close together as possible while pushing them as far away as possible from all the other negative examples in the batch. The whole thing just boils down to contrast. Now, this general idea of contrastive learning, it wasn't brand new. So why did SimCLR work so much better than everything that came before it? Well, the researchers were incredibly systematic, and they found 3 key ingredients that were the real secret sauce. First, the composition of the data augmentations turned out to be critical. If you only do something simple like random cropping, the model can actually cheat. It can just learn to match patches that have a similar color histogram. But, and here's the clever part, when you combine cropping with really aggressive color distortion, that simple trick is useless. The model is forced to learn about the actual shapes and objects. The second big breakthrough was in the architecture. They added a small extra network called a projection head right at the end of the main network, and the output of this head is what's used for the matching game. Its entire job is to learn to be invariant to the augmentations, to see past things like a weird color shift or a specific crop. And here is the truly genius insight. While that projection head is great for the matching game, it has to throw away a lot of useful information to do its job. But the representation from the layer right before it, oh, that is packed with all the rich features, including the color and texture the head was trying to ignore. So once the model's trained, you just snip off the projection head and use that more powerful, detailed representation for your actual tasks. It's brilliant. And finally, the third discovery was pretty simple. More is better. A lot better. Using much larger batches of images gives the model way more negative examples to contrast against in every single training step, and training for longer with bigger, more powerful models allows these self-supervised methods to really shine, closing the gap with supervised learning dramatically.
So you take these three simple but incredibly powerful ideas, you put them all together, and what do you get? You get some absolutely stunning results. Let's look at the numbers.
This chart shows the performance of different self-supervised methods on the famous ImageNet benchmark. As you can see, SimCLR didn't just inch past the old state-of-the-art, it blew right past it. It ended up matching the performance of a fully supervised ResNet 50. This was a huge moment for the field.
But here's the number that really turned heads. 1%.
With just 1% of the ImageNet labels available for fine-tuning, SimCLR achieved an accuracy that was better than the legendary AlexNet model, the one that kicked off the entire deep learning revolution. And it did it while using 100 times less labeled data. It's an incredible testament to how much signal you can pull from unlabeled data alone.
And this wasn't just an ImageNet trick. When they took the features learned by SimCLR and applied them to a whole bunch of other datasets, classifying food, aircraft, you name it, it was often better than a model that had been supervised on the full ImageNet dataset from the get-go. This showed that the representations it learned weren't just powerful, they were more general and more flexible. The strength of SimCLR is really in its simplicity. It proved that with a few clever ideas, we can unlock the potential of the mountains and mountains of unlabeled data all around us. It fundamentally changed the economics of building powerful AI. And it leaves us with a really exciting question. If AI can teach itself to see, what's it going to learn to do next?